Welcome to students. So, in the previous class we had looked into toral automorphisms. We had seen some properties of toral automorphisms like what are the basic periodic points and also that they are topologically transitive. So, as such toral automorphisms tend to be chaotic systems, but today we will be looking into more aspects of chaos of toral automorphisms. Now, since this is some kind of a homeomorphism in a two-dimensional space, so this forms a very nice example of a chaotic system in two dimensions. So, let us now recall toral automorphisms and we can look into the general definition of toral automorphisms. So, let X be say Rn upon Zn. So, it is basically Tn denoted as Tn be any n torus or be an n torus because there is only one n torus. So, this is an n torus. For any n you can think of any n in Z, n greater than 1, and let A equal to Aij be an n cross n matrix with integers with entries in Z and with determinant of A not equal to 0. So, this is an invertible matrix that we are looking into with integer entries. Now, we can define for such an A and for Rn, we know that any matrix will give us a linear transformation on Rn. So, define a linear map say L from Rn to Rn as L of you have this vector x1 x2 xn is basically A of x1 x2 xn. Now, we know that very well any linear transformation in a finite dimensional space can be given in terms of a matrix. Now, since A is an integer matrix, it maps Z onto itself. So, A maps, I should say that if I have Zn, right, A maps Zn to itself, and since A maps Zn to itself, we can think of A as allowing us to define a linear transformation, allowing us to define a transformation on the n torus. Let T equal to Ta, right, from Tn to Tn be defined as T of say I have x1 x2 xn transpose is same as A of x1 x2 xn transpose mod 1. So, this gives us, so we look into this particular mapping and we first check that this mapping is well defined. So, T is indeed well defined. Since if I have x and y belonging to Rn such that they determine the same point in Tn, then Ax mod 1 will be same as Ax Ay mod 1. The reason here is supposing x and y are 2 points in Rn which determine the same point in Tn, that means I can write my x as say y plus some integer m, and hence they will be basically, since these they differ by an integer, right. So, they give you the same point in Tn, and then you apply A on both the sides, you get Ax equal to A of y plus m, which basically happens to be equal to Ay plus Am, and if you look into Am, this is all having integer coefficients, right. So, if I try to take mod 1, right, so this becomes Ay mod 1, right. So, this disappears in that pass. So, if 2 points determine in Rn determine the same thing, so this basically this mapping T is well defined. So, this mapping T is a linear endomorphism. So, T is now a linear endomorphism. But if you look into general T, right, T need not be invertible. The reason is the way we have defined T, right, T heavily depends on A, and the entries of A are all integers, right. That is what is actually helping us in saying that this A, right, is basically mapping points of Tn into Tn. But if we try to look into T inverse, right, T inverse need not be, I mean T need not be invertible, because T inverse would basically come up from some matrix A, right. If you are looking into the linear transformation, it would come up from some matrix A which need not have integer coefficients. But the scenario completely different if we take determinant of A to be plus or minus 1, right. In that case, your A inverse will also have integer coefficients or integer entries. So, we see that this T, this map T is in general not invertible. However, if your determinant of A is plus or minus 1, then A inverse exists, and is an integer matrix. And what can you say about T inverse? Then my T inverse x1 x2 xn can be written as A inverse So, now we have an invertible endomorphism, right. So, we can say that our T is a linear toral automorphism. So, T is a linear toral automorphism. And we now want to look into whether this is a hyperbolic toral automorphism or not, and we have seen this earlier. So, we say that T is a hyperbolic toral automorphism if A has no eigenvalues of absolute modulus 1. So, in that sense we say that T happens to be a hyperbolic toral automorphisms. And as we had seen in the previous lecture that a hyperbolic toral automorphism is Devani chaotic. What we will try to see is, again we will try to look into the chaos of a hyperbolic toral automorphisms. What we will try to determine is what is the topological entropy for a hyperbolic toral automorphism. In fact, what we are not going to look into is that a hyperbolic toral automorphism can also be conjugated with, say if I have an n torus, then a hyperbolic toral automorphism can be conjugated with a symbolic system on in n symbols, and that gives you like lot of properties, because you can think of lot of properties over there, because again we know that our symbolic system is some kind of a invertible system, right, and if you are looking into a subshift of finite type, we know that it has various other properties. So, we can think of conjugating this to an n dimension in a symbolic system in n words in an alphabet of set n, but we are not going to get so much into details here. All we will look into what is the topologically entropy of a toral automorphism. Now, as such, for any dimension we can calculate this part, but it becomes easier to demonstrate it in case of 2 dimension. Our eyes are more used to seeing 2 dimension. So, what we will do is we will look into the simpler case of a 2 dimensional toral automorphism. So, we start with a simpler case. So, we look into the simpler case. Hyperbolic toral automorphism. For that we need some, let us build up some notations. So, let A cross A, sorry, A2 cross 2 be a matrix. So, let it be a hyperbolic matrix. With integers entries, and determinant of A is plus or minus 1. Let lambda 1 and lambda 2 with mod of lambda 1 greater than 1 and mod of lambda 2 less than 1 be the 2 eigenvalues of A, and let V 1 and V 2 be the corresponding eigenvectors. So, now as we have seen, what happens here is that you have t from t square to t square defined as, say you have x 1 and x 2, and under t they are mapped to a times x 1 and x 2 mod 1. So, this is a hyperbolic toral automorphism. Now, we will try to see a theorem here, and that is what we are going to do in this particular class. So, we will look into the theorem. The topological entropy of the 2 dimensional hyperbolic toral automorphism is given by log of lambda 1, or I should say log of modulus of lambda 1. So, the topological entropy of a toral automorphism is log of mod lambda 1, and since lambda 1 happens to be the larger eigenvalue of a toral automorphism, we know that the topological entropy is positive and hence the hyperbolic total automorphism is chaotic. So, let us now look into the proof of this part. Now, we know that we can start with our topological entropy, we can start the definition with either of the two definitions. We can either use the Edler's definition, since this is a torus is a compact metric space, we can either use the Edler's definition or we can use a Bowen's definition, but here it will be easy for us to use the Bowen's definition. So, we will use the Bowen's definition. Of topological entropy. So, now for Bowen's definition, all we need to find out is some n epsilon separated sets. So, let us start working it out. So, we first fix an epsilon. Now, we can cover T square by epsilon balls centered at a finite set say my finite set is x1 y1 xk yk. Now, when we are looking into epsilon balls, this is our T square is compact, right. So, it will have a finite epsilon net, but when I am looking into covering it by epsilon balls, I am defining my balls not using any metric. So, there is a different kind of metric that we are trying to use over here, or I would say that the definition of balls here is slightly different from what you could see as an ordinary say ball of radius epsilon centered at this points. We are taking a slightly variation, we are taking some variation in the definition. So, how do we define a ball here is, see around each point x1 y1, say around each point xi yi, for each of these I, we define a box so my box is Bi, which is basically xi yi plus alpha times V1 plus beta times V2 such that minus epsilon is less than or equal to alpha beta is less than or equal to epsilon. So, this is a kind of box that we are using. So, one can think of this in terms of say we now have at each point we have two directions, right. We have this linearly independent directions V1 and V2, and along each of these directions what we are trying to do is we are trying to take minus epsilon epsilon around one direction, minus epsilon epsilon in another direction, that gives us a kind of a box. And we can think of very well, we can think of this to be defining our open spheres, right. And as we know that our space is compact, there are finitely many of them which cover the whole torus. So, here my V1 and V2 are eigenvectors corresponding to the eigenvalues now. We keep in mind that when I am talking of lambda 1, my mod lambda 1 is greater than 1 and lambda 2. So, here my mod lambda 2 is less than 1. We know that these boxes, right. So, we can think of this as an epsilon net x1 y1 xk yk, and so these boxes Bi can be taken to cover T square, right. So, how many number of boxes you have? You have number of boxes, your boxes are covering your T square, they are covering your torus. So, let us try to see how a typical box is. So, say we are looking into, say for example, this is our unit square, and in this unit square we are typically having, supposing this is my point xi yi, then I have two directions and in both these directions I am looking into minus epsilon epsilon. So, this is basically giving my box Bi. So, this is my box Bi, and then along every such point, right, I would be having some such boxes, right, covering the whole of torus, right. We can think of such boxes covering the whole of torus. So, these boxes they cover the whole of torus, and we have a typical box Bi where you have one direction. So, you have this longer direction basically in the direction of V1, right, the shorter direction is basically in the direction of V2. So, typically I can write my Bi. So, supposing this is the box Bi, so this is basically the box Bi, and we have this point x1 y1 lying over here, xi yi lying over here. So, you have xi yi lying over here, and we know that this is basically the direction of V1 and this is basically going in the direction of V2, right. And we may not have seen this, but what we will try to do here is, when we take our eigenvectors V1 and V2, let us also assume that the magnitude of V1 is 1 and so is the magnitude of V2. So, basically let us take our eigenvectors to be unit vectors, right. So, we can start with our eigenvectors to be unit vectors, so that we do not have to worry about whatever length it is, right. These are unit vectors. For us what is important is the direction. So, we start with them, our eigenvectors to be unit vectors. We have this boxes Bi, and now let us consider the set of points Ci. So, consider the set of points Ci where I am defining my Ci to be the set of all points of the form xi yi plus j times epsilon upon mod of lambda 1 to the power k in the direction of V1, such that your j lies, so j takes all the values between, you have minus, now you are looking into, so you have mod of lambda 1 to the power k, you are looking into the integer value of mod of lambda 1 to the power k. So, from minus integral part of mod of lambda 1 to the power k to the integral part of mod of lambda 1 to the power k, you have these many points. So, these are basically 2k plus 1 points, right. So, you are looking into these points here. Now, sorry, not 2k plus 1, this would be exactly 2 times mod of integral part of lambda 1 to the power k plus 1. So, you are looking into these points, we are considering these points Ci. Now, what are these points Ci over here, if I want to see that? So, basically in the direction of V1, right, we have these points here. right. So, these are the points in the direction of V1. So, basically we are looking into these points. So, our Ci basically typically is a subset of Bi, it is in the box. So, all these points Ci are from the box Bi, and what is the cardinality of Ci? So, we look into the cardinality of Ci. The cardinality of Ci turns out to be twice the integer value of mod lambda 1 to the power k, right, plus 1. This is basically the cardinality of each Ci. Now, we want to claim something. So, what we claim here is take C to be the union of all such Ci. So, we are looking into Ci with I going from 1 to k. So, C is a k twice epsilon separated set for t square t. So, we claim that this happens to be a k twice epsilon separated set. We first prove this claim. So, we note that for any point ZW in t square we can choose some I say we know that we have this k boxes, right. So, basically our ZW will be lying in one of these boxes, right. So, we can choose some I such that your ZW lies in this box Bi, because Bi's cover the torus, and so since the property of Bi is it contains all those points which are at a distance alpha times V1 plus beta times V2 from xi yi. So, we can say that your ZW is xi yi plus alpha times V1 plus beta times V2 for some alpha beta which lies between minus epsilon and epsilon. So, now we are fixing our alpha and beta also depending on this point ZW. If we choose our j such that you are choosing your j between minus lambda 1 to the power k, integer value of mod lambda 1 to the power k less than or equal to j less than or equal to integer value of lambda 1 to the power k. If you are choosing your j between this part, right, or I should say in this range, right, such that your mod of, because you have already fixed an alpha here. So, your mod of alpha minus j times epsilon upon mod of lambda 1 to the power k, if I am looking into this modulus. So, this modulus is less than or equal to epsilon by 2 mod of lambda 1 to the power k. Supposing I want to choose this j such that this inequality is satisfied. Now, if you look back into our figure, this you can always find such a j, right, because your ZW lies somewhere over here, right. So, you have these points j, so these are basically your points j, right, and since they will be lying somewhere over here, I can choose that particular value of j for which this inequality is satisfied. So, this is possible, and then we let now I am taking my point Zj Wj to be equal to this xi yi plus j times epsilon upon mod lambda 1 to the power k times V1. So, if I choose this part, then this point with this particular coefficient, this j here, right, this will be basically a point of Ci. What remains to see is that this happens to be a separated set. So, take any ZW in Bi, right, you have some j, right, for any ZW in Bi you have a j for which this inequality is satisfied, and in that case you can always choose a point Zj Wj, right, in Ci, which is basically having, which has basically this equation, right. So, it is basically your point Zj Wj can be fixed, right, for a given j once you know what is your Zw. So, now given a Zw, basically given a Zw, we are choosing a Zj Wj in Ci or in C. Now, since your Zw could be in any Bi, right, for any Zw in the torus, you have a point, you are fixing a point of C. Now, for what happens is 0 less than or equal to r less than or equal to k, what happens here is we have Tr of Zw is basically Tr of Zj Wj, right, plus I have alpha minus j times epsilon upon mod lambda 1 to the power k times a to the power r V1 plus beta times a to the power r V2. So, this is basically my Tr Zw, and hence if I am looking into this equation, so I want to say that this is basically this equation, and according to this equation what is my mod of Tr Zw minus t to the power r Zj Wj. This modulus would be less than or equal to, now we again come back to this equation, right. So, I am taking this on the other side, what is this modulus? So, this modulus will be less than or equal to modulus of this part, but now if I look into my V1 and V2, these are both are linearly independent, right. So, the modulus of this factor will be basically less than or equal to, I can take the modulus of this and take the modulus of that. Again your V1 happens to be a eigenvector for AR, right. So, AR V1 would be same as lambda 1 to the power r V1 and AR V2 would be same as lambda 2 to the power r V2. So, what happens here is, what is this modulus? This modulus is less than or equal to, we have this modulus of alpha minus j times epsilon upon mod lambda 1 to the power k times lambda 1 mod lambda 1 to the power r plus mod beta into mod of lambda 2 to the power r. We have already taken our V1 and V2 to be unit vectors. So, the modulus of them will be 1. So, what is this less than equal to? I can say that this would be less than or equal to, we have already taken what is this part, right. We have already assumed that we are choosing our j so that this particular modulus is less than epsilon by 2 mod lambda 1 to the power k. So, what we have here is, this is less than or equal to say epsilon by 2 mod lambda 1 to the power k into mod lambda 1 to the power r plus you have mod of beta, right, to the power lambda mod lambda 2 to the power r into mod lambda 2 to the power r. Now, think of this factor, your lambda 1 to the power r upon lambda 1 to the power k, right, this quantity is less than 1. This is basically mod lambda 1 to the power, or I should say 1 upon mod lambda 1 to the power k minus r, this quantity is less than 1. So, I can say that this would be less than epsilon by 2. what happens to this quantity? We know what is our beta, where is our beta lying? It is lying between minus epsilon to epsilon. So, mod beta at the most can have value epsilon, and if I look into mod lambda 2 to the power n, right, mod lambda 2 is less than 1. So, mod lambda 2 to the power r is also going to be less than 1, right. So, this is less than epsilon, right, and in all we can say that this would be less than twice epsilon. So, what we have here is that our C happens to be, hence C is a k twice epsilon separated set. And now what is the cardinality of C? So, if you look into the cardinality of C, so the cardinality of is at most twice, right. We had seen what is the cardinality of Ci. So, the cardinality of Ci happens to be at most integer value of lambda 1 to the power k plus 1, right. This was the cardinality of Ci, but if I look into what is the cardinality of C, there will be k such Ci, right. So, the cardinality of C happens to be this factor, which gives an upper bound of, we know that we want to look into the maximum cardinality of an k twice epsilon separated set. So, this gives an upper bound for that maximum cardinality. So, k epsilon t, right, of the k twice epsilon separated set in T square, right. So, in the torus, and hence what we have is the topological entropy happens to be equal to limit as epsilon tends to 0, right, limit as k tends to infinity, right. I have 1 upon k log of r k, sorry, this is twice epsilon t, and this turns out to be less than or equal to limit as epsilon tends to 0, limit as k tends to infinity, you have 1 upon k times log of, because this quantity is having this as an upper bound, right. So, I have log of k times 2 twice integer value of lambda 1 to the power k plus 1, and if I want to look into that factor, right, if I try to take this limit as epsilon tends to 0 and this limit as k tends to infinity, this turns out to be equal to log of mod lambda 1. And so, the result that we have here is that your entropy of T is less than or equal to log mod lambda 1. Now, this is one way, right, as we have seen this is just in a single direction. We will try to look into this inequality the other way around also. What we had done is that we had found out the upper bound for an n2 epsilon, for a k2 epsilon separated set. We can find similarly, we can find a lower bound also. So, that would give us the reverse inequality. So, we fix an x y in T square and for epsilon greater than 0 and k greater than equal to 1, we consider D to be equal to the set of all x y plus say j times 2 epsilon upon mod of lambda 1 to the power k times V 1, right, such that your j varies from minus integer part of mod lambda 1 to the power k to the integer part of mod lambda 1 to the power k. Let us look into this set D. Now, our claim here is D is a k 2 epsilon upon mod lambda 1 to the power k separated set. So, take any two distinct points A1 and B1. So, take two distinct points say A1 B1 and A2 B2, and let 0 less than or equal to r less than or equal to k minus 1. So, what we have here is mod of t to the power r A1 B1 minus t to the power r A2 B2. This is basically mod of, I am looking into this factor, it is basically mod of j. So, I have this A1 B1 and I can write my A1 B1 as this factor, write some j here. So, this is basically j times 2 epsilon upon lambda 1 to the power k A1 B1, and I can take my A2 B2 to be basically this plus I times 2 epsilon upon lambda 1 to the power k. So, this would be some j minus I times 2 epsilon, right, upon mod lambda 1 to the power k, right, into t to the power r of V1. And this we can very well see that this would basically be, should say it would be less than or equal to, or basically this will exactly be equal to, this is twice. Now, I have twice mod j minus I epsilon, right. I have lambda 1 to the power k here. So, and I have this is again lambda 1 to the power r here. So, this would be upon mod lambda 1 to the power upon k minus r. So, I am thinking of this part. So, this would exactly be equal to this factor. So, if I take my set S, so if I look into my S k epsilon t, this happens to be the cardinality of D, and the cardinality of D is twice, right. Again I have integer value of lambda 1 to the power k plus 1, right, is a lower bound of a k epsilon separated set. I can think of, because this was just a constant, k epsilon separated set. In t square, and hence what do we have here now? So, the entropy of T is basically limit as epsilon tends to 0, limit as k tends to infinity, 1 upon k log of S k epsilon t, you can think of that part, and that becomes greater than equal to, because I just know a lower bound for this term. So, this becomes greater than or equal to limit as epsilon tends to 0, limit as k tends to infinity. I have 1 upon k times log of twice integer value of lambda 1 to the power k, right, plus 1, and this is basically our log mod lambda 1. And hence, from this equation we get that the topological entropy of T is greater than or equal to log mod lambda 1. We look into this fact, the first time we proved that topological entropy of T is less than or equal to log mod lambda 1. Now, we have a result saying that topological entropy of T should be greater than or equal to log mod lambda 1, and that proves that topological entropy of T is basically equal to log mod lambda 1, where lambda 1 happens to be the eigenvalue with modulus greater than 1 for the hyperbolic matrix A. And I hope this is clear to all of you. So, your hyperbolic toral automorphism is a chaotic system. We will look into more chaos in the next class.